Okay, so try to find the equivalent of this. Four ohm, 6 ohm, and 8 ohm. A, B, and A and B. Okay. Now you have to find R, A, B. Just tell me, how are these 2 points? Are they same or different? Are they same points or different points? So look, here we have a path. Due to this path, these 2 points are connected, right? This is a short circuit, and then this point and this point will have the same potential. Therefore, it will act more like two same points. And how about these 2 points? Those 2 points are also similar, right? Now, what I'm going to do is here, this is a bit complex. When I look at this, I don't get an idea how to solve. I'm not able to find something in series or parallel. Okay, it's a bit confusing. Therefore, what if I rearrange this? I'll again mark the points A, B, A, B. Now I'll look the first resistor. First resistor is connected between A and B. So I'll draw the first resistor connected between A and B. Now I'll go to the second resistor. It is connected between B and A. So I'll draw between B and A. And the final resistor is connected between A and B. So now I can solve this. Did you get what I have done here? When this looked complex, what I did is I identified if there are two same points. And from that, I redrew the circuit in a convenient way for me. Afterwards, I'll simplify. Got this concept? Do you get the idea? Is the idea clear? Here, what we have done. This it's clear, right? Okay. Now, don't draw this. Now, can you identify any of the resistor that is in series or parallel? Okay, do you find any of the resistor in series or parallel? These two resistors, are they in series? Sorry, are they in parallel? These two, are they in parallel? No, right? It is not, because they are not connected to the same point. How about these two resistors? This resistor and this resistor. Are they in series? They are not, because the current flowing through this might divide into each branch. Therefore, the current through this and current through this is not the same, right? Therefore, here, do you find any series or parallel combination? No, right? We don't have any. So let's use some other method to solve this resistor. So let's say I'll write a note point when series or parallel, when series or parallel combination cannot be identified, cannot be identified, then some other techniques are used. Some other techniques are used Okay, some other techniques are used. Considering the symmetry, considering the symmetry is an important technique. Is an important technique. Okay, so let's say we have a circuit like this. Here, do you observe a symmetry? I observe a symmetry just like this. This is my point A and B. Between A and B, about this point, I observe a symmetry. Do you all? I'll consider this one as R by 2 separately. Then I observe a symmetry about A and B perpendicular to it. Okay, so I'll say when symmetric axis, when symmetric axis perpendicular to AB, then current in similar branches, current in similar, correct, then the current flow, then the current flow is similar in corresponding branches. What does that mean? Now just think here, let's say the potential difference between A and B. The potential difference between A and B is 10 volts. The path, this is the center, okay? This is the center. When you come from here to here, there will be a drop of 5 volt. And here also you will have a drop of 5 volt because it is similar, right? So the drop also has to be similar. Let's say the drop here is 3 volts. Then this side is also just the same, right? It is looking the same. Therefore, here also it will be 3 volts. Then the current in this branch and this branch is similar. Got it? So it's just like this. Let's say the current in this branch is I1. Then here also it is going to be I1. If the current in this branch is I2, then the current in this branch is also I2. And here, in similar branches, the current is same. That's the idea. So just think, if I remove this connection, if I remove the connection over here, will that make a difference? Okay, so here the current is I1. Here also it's I1. So here it's I2. Here it's I2. This is I3, sorry, I4, and here also it's I4. And here it's I3, and here it's I3. Look, because you have removed this connection, did it make any change to the circuit? Or it is still identical? It's still identical, right? Now can you solve this? So I'll divide this resistor to R by 2, R by 2. Now can you solve this? Do you find anything in series, parallel? Yeah, these two are in series. These two are in series. So this combination is parallel. And then series. And then parallel. So we can solve. Is the idea clear? So note this down. Is similar in corresponding branches. Then removing the connection as shown won't make a difference. Won't make a difference. And there's one more thing important. Along this line, the potential is same because it is exactly halfway. Therefore, between these 2 points, if it is 10 volts, here it should be 5, and at the center it's 5. Okay, so we can tell the potential along the symmetric axis, is same. Noted. If you'll have noted, try this example. Here, just first tell me, can you solve this using series parallel rule only? Do you find anything in series or parallel? There is no anything in series parallel. Okay, but still we have a symmetric. We have a symmetric axis. What can you tell about this resistor? What can you tell about this resistor? Will this resistor work or it won't? So you must think, will there be a current flow through this resistor? It won't. What is the reason? It won't work. What is the reason? No potential difference, right? So what you can do, you can just remove that. But you can just remove this. So now can you solve? Now do we have series parallel? Okay, clear up to this. You understand how to use the symmetry. Noted. Shall we move to the next one? Next, next we can have a symmetry that is parallel to AB. Now here, in this example, we have both symmetries. But let's consider the parallel symmetry. This is my symmetric axis. So here what we can do is, now you should have got an idea about how current flows. Now the current, look up and down, both directions, it is almost having same resistance, right? Same resistance. Therefore, current will equally divide. Okay, the current will equally divide. And I'm not drawing the current in each and every branch, but you must understand the current will equally divide. So if current flow is equal, what can you tell about the potential drop? This potential drop is V. This potential drop also will be V. So the potential over here will be same. And if I check the potential at these 2 points, it also will be same. So can I bring them closer? Can I fold this? Bringing them closer means folding them, right? So can I do that? Can we fold? Will it make a difference? No, right? As we discussed previously, if we have two same potentials, what we can do, we can bring them closer. Okay. Okay. Now, if you look across above this resistor, when I folded, I didn't get a resistor above this resistor. So this will remain as R. This also will remain as R. But above all the other resistors, we got one more resistor. Therefore, this becomes R by 2. R by 2. Is it clear? So let's write a note. Symmetric axis is parallel to AB, then the current flow above and below, current flow above and below the axis is identical. Thus, the potential, thus the potential at at corresponding at corresponding points are identical. Corresponding are identical. Therefore, can be folded about the axis to bring those points closer, Once you have noted, let me know. How about the others? Tara and Shahama, noted. Next, let's note a subtopic. Equivalent resistance of resistors in a cubic network. Cubic network. We have to find the resistance between A and B. So here also, do you see anything in series or parallel? No, right? What we can do is let's look from bottom. I'm looking from bottom. When I look from bottom, my setup or system will look something like this. Do you agree? When you look from bottom, it will look like this. Just think like looking into a box and you see these edges. So when you look in, so this is a box. When you look from bottom, these are the edges. Okay. This edge is your base and these are those side edges. Okay. So in each of those edges, we have resistors. So do you agree with me? It will look something like this. Now, how can we solve? Still, we don't find anything in series or parallel, but we must be able to solve now using symmetry. Using symmetry, we must be able to solve, right? So you can consider a symmetric axis like this. Or let's first consider a vertical symmetry. What do you say? Here we have a vertical symmetry, right? So considering the vertical symmetry, I'll say the potential in this line is same. Potential same along this line. Using that, what I can do is I can remove this resistor and this resistor, right? Now you can solve. So if we remove these two resistors, this is 2R, this is 2R, here 2R, 2R, that's R. So I think we get 2R, 3R, and 2R. Two R, 3R, and 2R. See if you have got this. So this is identical. R and R is 2R and 2R is R. Next, 2R by 4. Got this? Noted. How about the others? Did you all get it? What I said here. You can consider a parallel symmetry also. If you want, you can fold this and solve. Maybe you can try by yourself. We have only 1 more minute. I hope what we did today was clear. I did it a bit very slow because you need some time to understand and try by yourself. And this is very important. So are you clear with the section we did today? Have any doubts? We have a few more resistive networks to discuss under these cubes and delta to y transformation. The delta to y transformation, we don't get questions nowadays and it is not in syllabus. Still, let's just look how to obtain the equations. So for today, is it clear? Any doubts?